Hello and welcome to Intermediate Algebra, Unit 6, Lesson 4. We're going to talk about factoring completely and what that means. And essentially we're going to take all of the things we've done in this unit about factoring and put them together so we can approach any problem that asks us to factor completely. So we're going to look at many forms of polynomials here, and there'll be a little summary about how the number of terms can help you figure out where to start. But pretty much the objective is to put all of our factoring methods together. So always we look for a common factor. And when you take that common factor on the outside of the parentheses, you look inside, see what's left, and look at the number of terms that are in that polynomial. If it has two terms, your choices are difference of squares, a sum or difference of cubes. If it has three terms, it might be the square of binomial, or you'll use some other method of factoring a trinomial, either by trial and error or grouping. And if that leading coefficient is 1, we know that's a little easier. If it has more than three terms, you're going to try grouping most of the time. So once you get a factor that's in parentheses that has multiple terms, you want to check to make sure it is done being factored. If it can be if that factor you get inside the parentheses can be factored, you need to keep going. So first, for two terms, this is probably the easiest. The first thing you do is remove any greatest common factor. And my experience says that on the test, the problems with two terms where there is only a common factor and nothing else, like if I did 2 plus 4x squared and said factor, all you can do is take out the 2. It becomes 2 times 1 plus 2x squared. And then you're done, and that's very confusing to students. So always look for the common factor first. With two terms, you may or may not be done. If there's addition involved, you will be done once you remove the common factor. So if you get the sum of two things, you don't even care if they're squares. Once you remove the common factor, it doesn't factor any further. Now, if it's subtraction, you want to look after you remove the common factor to see if what's left is the difference of two squares, and if so, apply that pattern. Or is it, well, you're not done if it's a sum. I guess you would have to look, I take that back. I said you're done if it's a sum when you remove the common factor of two terms. You need to look and see if it's the sum of two cubes, because that can be factored. But if it's the sum of two squares, or if it's not the sum of two cubes, you'll be done. But if your remaining expression is the sum of two cubes, use the formula for that, which we had in other lessons. And if it's the difference of two cubes, use the formula for that, which we had in those same lessons. Now, if you have three terms, you still have to remember to remove any common factor. That step's often forgotten, and it makes the problem either impossible or very difficult. Now, if the quadratic and constant terms, if you put the polynomial in standard in the usual order, it'd be the first and the last terms. If those are perfect squares, then see if the middle term makes it fit the pattern for a binomial squared if you're looking for a shortcut. But even if you don't do this step, you can always just go to one of the techniques for factoring trinomials. So if the squared term is a coefficient of 1, that's a little easier. If it's more than 1, you can use guess and check or break up that middle term and turn it into a grouping problem. If you have 4 or more terms, the first thing you need to do still is to remove any greatest common factor that's in all of the terms. And after you look for that and either find it and take it out or don't find it, then you factor the remaining terms by grouping. If you have 4 terms, it's going to be 2 pairs. That'll be the most common one you'll see. But if you have 6 pairs, you might set it up in 2 sets of 3 if you arrange it so it looks like you can rearrange the terms so you have 2 trinomials that factor. You could do 3 sets of 2, but that's less typical. So you factor each group, and then once you have the groups factored, you look at each of them as an individual problem. Then you look to see if you have a binomial factor or something in parentheses if there's a factor that shows up in every term. So just make sure none of those can be factored further. We'll see an example of that at the end. So first example, I look at the problem and I say, what's the common factor, if any? I have 10a squared x minus 40b squared x. Well, the 10 and the 40 have a 10 as a common factor. 10 times 1 is 10. 10 times 4 is 40. I don't only have an a in one term, so that won't be a common factor, but I do have an x in both terms, so that becomes part of the common factors. The greatest common factor is 10x. I put that out here, and then what goes in here is 10a squared x divided by 10x would leave me with an a squared. Or the other way to look at it is, what do I need to multiply by 10x to get what I started with in that first term, that 10a squared x. And then for the second term, 4b squared times 10x will give me 40b squared x. Now I need to look at what's in the parentheses. There are two terms. This is the difference of two squares. The first one is lowercase a squared, and the second one is 2b whole thing squared. So for my pattern, a plus b times a minus b, I have big A is in this case little a. This is a little confusing. And the second perfect square comes from squaring 2b. So I do 10x times a minus 2b times a plus 2b. I look at each of these sets of parentheses and I realize I am done. Those are prime. Example 2. Now, we're used to seeing things squared, but remember, if you have an even power, it can be written as whatever the power is, cut in half, that whole thing squared. So x to the 6th is x cubed squared, and y to the 6th is y cubed squared. So first I look for a common factor. There is none. Now I have the two terms remaining. They're subtracted and they are perfect squares. Now they are also perfect cubes, but it turns out it's easier to factor them first as perfect squares. And then what I get is if a is x cubed and b is y cubed in my difference of two squares formula, I get x cubed plus y cubed. Oh, that's the sum of cubes, times x cubed minus y cubed. Oh, that's the difference of two cubes. So this first pair of parentheses here is how that sum of two cubes factors, and the set of parentheses here is how the difference factors. So I get x plus y in parentheses times x squared minus xy plus y squared, all in parentheses. Another set of parentheses x minus y, and another set of parentheses x squared plus xy plus y squared. And because these big parentheses with the trinomial in them come from factoring a sum or difference of cubes, I know that that does not factor any further. So example 3, there is no common factor. I have an x squared and a 2 squared, but they're added. The sum of two squares does not factor. If I factor this as x plus 2 whole thing squared, I have to remember to FOIL to check. So I'd get x plus 2 times x plus 2, and I will have a middle term of 4x when I multiply those out. And I don't have that there, so this cannot factor as x plus 2 whole thing squared. That means something different than squaring the x and then squaring the 2. So in this case, this is what we call prime. It doesn't factor anymore. So here's some for you to try. The big hint I would give you is look for a greatest common factor first. So try these, stop the video, write these down, and try them, and then we'll look at the answers and discuss them a bit on the next slide. See you in a minute. Alright, you're back, so I trust you tried these. So for number 1, I had to take out a common factor of 2 first. And when I do that, I was left with 2 times 1 plus 4x squared times 1 minus 4x squared. But 1 minus 4x squared factors as the difference of two squares, which is where the 1 plus 2x times the 1 minus 2x comes from. Alright, number 2. Factor out a 7, and it leaves me with 7 outside of parentheses, a to the 6 minus 1. I'm going to factor this one similarly to how I did x to the 6th minus y to the 6th. I'm going to do the difference of two squares first, where I have a cubed squared and 1 squared. And when I do that, I get a cubed minus 1 times a cubed plus 1, and that becomes the difference of two squares which factors like these first two parentheses, and the sum of two squares which factors like the last two sets of parentheses. Okay, so that's how that one goes. When we get something to the 6th power minus something else that can be written to the 6th power 1 to the 6 is 1, we end up with this two-step process. So for problem number 3, I've got 4 terms. First thing I see, but I look for a common factor first. I don't have an x in every term, so that won't work. I don't have 3 and 4 going to 12, but there's nothing in front of this one, so there's no common factor. The other thing is, I can rearrange if that makes more sense, but you can just try pairing these as they show up. So if I pair these, it's nice. They're all addition. I don't have to worry about that sign change in the second set of parentheses. 3x plus 12 is a pair. 4x plus x squared is a pair. So for the 3x plus 12, I can remove a factor of 3, and I'll be left with x plus 4. 4x plus x squared, I can remove a factor of x, and I'm left with 4 plus x. Now, x plus 4 doesn't look the same as 4 plus x, but addition has a property that order doesn't matter. If you're adding positive numbers, the order doesn't matter. So 4 plus x can be written as x plus 4, and that's what I've done here. So here I get the 4 plus x. I just did the same thing. So I just ignore the order, or I, in my mind or on my paper, rewrite this. So that leaves me with the 3 plus x from the coefficients of the parentheses, and the x plus 4 was a common factor. Number 4 is a little more complicated, so I'm going to show you the steps here. I had 6 terms, so I know I have to start with grouping. It's more than 3 terms. And it was set up nicely, so I see that, I'm not going to group t's with d's if I don't have to. And anything with a c, a d would go with something with a cd. So I just grouped these into 2 sets of 3. And if you look at the second set of 3, I had to change all those signs. Let's go back and see what the problem statement was. So I had a minus t squared. All of these were negative. Oh, did I not do that correctly? I might not have done that correctly. I needed to change these signs. Sorry about that. That's a plus 8. That's a plus 16. Everything in here should be positive. I apologize for that. So this is wrong. Mark that down as wrong. It should be plus plus. And then this becomes plus 4, and this becomes t plus 4 squared. Now, forgetting about the fact that those are now pluses, keep that, that's a plus. Keep that in mind if I had done that sign change correctly. If I look at this, I can write c plus d times c plus d as c plus d whole thing squared. And this was a t plus 4 times a t plus 4. I can write that as t plus 4 whole thing squared. These are subtracted. I now have the difference of 2 squares. This is super tricky. On a scale of 1 to 10, this is like really hard, like a 12. But if you get the process, you should be able to do it and not make my mistake, hopefully. But so I have c plus d is the first thing squared. T, this is again a plus 4, is the second thing squared. So I have c plus d plus t plus 4, c plus d minus t plus 4. So this will be a plus and this will be a minus here. Those two signs will switch in the end. But that one is definitely a more complicated one. You won't have 12 of those on the test. If you have one, it might be just to see if you can do it. But that's how grouping works. It allows you to break things up into smaller problems. I just want to check. Yeah, I did make that sign mistake. I apologize. All right, I think that's all we have. It is all we have for this. So the factoring completely, you can see you have to be really careful, more careful than me. And you have to have some sort of methodical approach, and that methodical approach always starts with removing a greatest common factor. Thank you for watching, and good luck with your work in intermediate algebra.